and easily work out this integral, because this is going to be just 2r squared, and this will be r dr d theta. R goes from 0 to 1, theta goes from 0 to 2 pi, so constant limits. So whereas integrating over this ellipse would have been kind of a pain, here we map to a circle using this transformation that warps the ellipse into a circle. And that is the idea. These changes of variable are meant to make the region nicer than it was before. For instance, one of the examples in the notes maps a parallelogram into a rectangle. So that's generally the idea, is to get a familiar region that we know how to integrate over. So any questions about that one?
Would that way of doing it would be the only way or the best way?
Well, it depends on transformation, because and here it's convenient that the equation. So we have this equation here that defines the old region, so that we get a substitute. And so generally, that's what you're going to try to do if you have described by the equation. Now, one example that's in the notes is if you have a parallelogram, you can come up with the equations of the lines that define the edges of a parallelogram, and from those equations, you can come up with a transformation that maps the parallelogram into a rectangle. Because what you would get is, here, this edge might be defined by the equation ax plus by is equal to a constant. And here, it's a parallelogram, so same thing, ax plus by is equal to a different constant. So then you figure, well, let's let u be equal to ax plus by. So now you have a transformation that's going to map this into a rectangle where u is going to be between C1 and C2. So this is a nice standard technique when you have something nice like a parallelogram. You can do a similar thing with a trapezoid, although the transformation is still linear in nature, but it's going to be a little more complicated. So you'd have equations for these lines that involve different combination of x and y, and you can let v be equal to that. So you can do so that's one thing that you can do. Okay, actually,
In the notation,
yeah.
right there on the 2u squared plus 2v squared.
Yeah.
Then you go to the 4 over the square root of 3.
Uh-huh.
Should there be some notation? I mean, are you multiplying that by 2v squared, or is there?
Okay. Because we got all of this from over here, where so the Jacobian of a transformation turned out to be this 4 over square root of 3.
Right.
And then once we simplified all this is where this came from.
Right.
And then we have a du dv.
I understand that, but is there supposed to be a gap there?
No, all of this is multiplied together.
That's what I was asking.
Okay, yeah, it's all together one integral. Yeah. So. All right. Actually, this next example, which I have a few minutes for, illustrates what I was just talking about. This is from the same section, number 20. So we have integral x plus y e to the x squared minus y squared, where r is a rectangle. Instead of giving vertices, you're given equations. X minus y is equal to 0, x minus y is equal to 2, x plus y is equal to 0, x plus y is equal to 3. So here we have equations of 4 lines that define, so in general you get a parallelogram, but here this happens to be a rectangle. So it would be something like, so this gives you one edge, y equals x, y is equal to x minus y. Here's another, So this is your region R that you're integrating over as defined by these four equations. So this suggests, let's let u be equal to x plus y, v is equal to x minus y. So now you can, but here, you still have to describe your original variables in terms of the new ones. So this is not the right relationship to define the, to define a Jacobian. So you need to solve these for x and y. So if you do that, now these are linear equations, so that's something that you can do, right? What you get is x is u plus v over 2, y is u minus v over 2. So then you can use these to compute the Jacobian. So the Jacobian of a coordinate change, so these will be simple derivatives just like the last time. We're going to get 1/2 minus 1/2 minus 1/2 1/2. So we end up getting minus 1/2 from all of that. So that takes care of the Jacobian. It's just going to introduce a constant factor. But now we can rewrite the integrand. Okay. Over our new region, R tilde, so x plus y, that's just going to be u. And e to the x squared minus y squared, we can factor that exponent. E to the x plus y, x minus y. So this is going to be e to the uv times 1/2 du dv. So we've rewritten the integral in terms of the new variables. The only thing we don't know yet is what is the new region R tilde? Well, here we have x plus y is between 0 and 3. So that means that u is between 0 and 3. Similarly, x minus y goes from 0 to 2. So v runs between 0 and 2. So we've transformed this rectangle. Really what we've done, we've taken this rectangle and rotated it. In this case, we've rotated it 45 degrees in order to get constant limits on u and v. So really what we have is 0 to 3 and 0 to 2. So now we have this relatively simple integral to handle. Although, actually, it does require integration by parts, sadly, because it has u and then u and the exponent as well. But you guys know how to do that, right? Okay, so, all right, I've just run out of time. So I will be writing these examples up, plus ones from the last few lectures, and also one from cylindrical coordinates, but I never got around to doing in class. I'll write that up too. So I'll try to fit this in over break while I'm on the other side of the world. So, yeah, 3 weeks to do this test. So, yeah, 3 weeks from today. So even with spring break deducted, you have plenty of time.
Oh my goodness. You going to go for break, Zach?